Welcome back, everyone. Now let's talk about variation. Why do we need variation? Just imagine, you've been sitting an exam and on average students got 25 out of 50 points and you got 28. Are you pleased? Good question. Like some might say yes, others not so much. Well, basically that's you. Average is 25. Your average after all. Okay, you can be pleased, I guess. Well, if you assume the distribution was like that, that's average, and you are here amongst the top, 10%, 5%, then yes, you will be pleased. So the difference between those two is just the variation within the distribution. So how can we quantify variation? There's a few different ones again. The most simple one is range. So we take the smallest and the largest data point and we report that as the range. Obviously it's very susceptible to outliers. Just one very large data point and range is very big. More commonly used is the percentiles. You already know one, the median. That's the 50th percentile, meaning 50% of data points are smaller, 50% are bigger. Now we can create the same thing for any sort of percentage. So the 10th percentile means 10% of data points are smaller, 90% are bigger. 80th percentile, 80% smaller, 20% bigger. If you know a few of these percentiles, then you know quite a bit about the distribution and its width or its variation. Most commonly used, maybe some of you have kids, know this chart. So this is the age here, going from left to right in months. And there's, for example, the weight. And then you can look up, okay, let's say you've got a kid that's 1 year, 12 months. The median, the 50th percentile, is at just above 9 kilos. If your kid weighs 11 kilos, then if you follow this line, you're in the 90th percentile. So you know that 90% of kids are smaller and only 10% are even heavier. So this immediately translates into sort of a curve where you know what it looks like. So 90th percentile means this is 10% and this is 90%. Here we are. This is a very handy way of describing the variation in a distribution, but one of the most well-known, and you've probably heard of it or used before, measures is the variance. Variance comes in like two slightly different types. The usual one that you use is the sample variance. I'll explain it in more detail in a second. Basically, if you know what the mean value is, x bar, this is the mean, then you take the difference of every data point from the mean, square it, and you sum that up over all data points. That's basically what you do in like both settings. Also in the population variance. To calibrate the whole thing, in the sample variance you divide by n-1, so number of data points minus 1. In population variance you only divide by n. Reason is, if you got all the data there is, like, I don't know, you've got a complete set of data, like all the marks in one class, and you just want to calculate the variance of your students, then you use n. That's kind of the normalizing number. But if you've just taken a sample, you kind of more thinking more widely, about generally kids in the whole country of that age, and you've taken a sample of 10 that are representative, then basically your variance will be smaller, because you also don't really have a real mean value. You basically just calculate one from your sample, so the mean value will be slightly off, making your variance smaller. And to compensate for that, roughly speaking, I don't want to show you the formal proof for this, you just divide by n-1. In a more like intuitive explanation, you could also say that 1 degree of freedom is lost by correcting the mean to the true mean, and then only n-1 degrees of freedom are left. And obviously there are different ways of calculating the variance depending on what numbers we've already calculated. Just to give you an idea how this whole thing works, let's say the whole population is numbers 1, 3, 5. So our mean value is 3. If I calculate the population variance, then obviously I calculate 1 minus 3 is minus 2, squared is 4. Yeah. 3 minus 3 is 0, no contribution. And then 5 minus 3 is 2, squared 4. Yeah, so we've got 8 divided by number of data points 3. So our population variance is 2.66. Now, if we only have a subsample of this, if we only got the data points 1 and 3, we're missing the 5, and obviously my sample mean value will be 2. So it's off by a little bit, meaning that my variance, if I calculate it, is like 1 minus 2 is 1, and 3 minus 2 squared is also 1. So I only get the variance of, so I get sample variance of 2, whereas I would get a population variance of 1. And you can probably see like the sample variance is not exactly, but it's a little bit closer to the true variance in my population, whereas the population variance for a sample gives us just the wrong number. Okay, you have a go. Determine the sample variance of this dataset, please. Excellent. And yeah, basically you need the mean value of 4, then 6 minus 4 is 2, squared is 4, and same with the 2, and with the 3 and the 5 you get a 1 each, so it's 10 over 3, 3.33. If you don't want to do it by hand with your calculator, you can use Excel. The commands are var.p for population variance and .s for sample variance. And obviously in MATLAB it's similar, there's like parameter behind. So sample variance is like the standard. If you just say var of x, it's using sample variance. And if you give a comma 1, you can convert it to population variance. The variance is widely used, but one issue with the variance is the unit. We calculate the difference and then square it, So if you measure something in centimeters, the variance comes in centimeters squared. If you want like a measure for variation in the same sort of unit as the measurement itself, you just need to take the square root. So that's the standard deviation. Standard deviation, commonly written as a sigma, is just the square root of the variance. And obviously it comes as sample variance and population, sample standard deviation and population standard deviation, just accordingly, same formula. Sample with like dividing by n minus 1 and population dividing by n. In Excel, there's a stdef command, and in MATLAB, it's called std, similar to the variance. Just a little note, because some of you might in the future be working on actual data for I don't know what your job is gonna be, but sometimes like you're working on papers of other people and they report numbers, they report variances maybe, or you have a collaborator and he doesn't want to send you all the raw data. So how can you join samples if you just know variances and calculate a joint variance? Well, here we go. This is the formula. It's quite complicated. N is easy. You just, if you have two subsamples, n1 and n2, you just add them. That's the total number of people. And the mean value of two samples with x1 bar and x2 bar is already a bit complicated, and yeah, the joint variance of two samples looks a bit hectic. So just put it there for your reference. We won't really need it any further. Great. So next video will be about two-dimensional data. See you soon.